I'm going to start. Hello again from my side. For those who are here in the audience, I guess I don't have to introduce myself, and also hello again, warm welcome to everyone who is joining online. Thanks to SimQ. I won't say thanks for the invitation, I guess, because it's our building here. But anyway, thanks for being part of this, to take part with a small presentation on our side. It's a bit of a repetition because I already introduced our software solutions in the morning, or you heard about that in the morning as well. So it's sometimes with a repetition, but I try to give you a different view on it and try to show you how we are using all those SimQ tools, all those softwares, and present it to our customers or use it in talks and consultations with our surgeons and the clinics. So the big question maybe, why do KLS Martin need simulation in CMF? There are different factors, which I already told you in the morning. First of all, it's time saving. So I guess I don't need to explain that the simulation is quicker than producing implants and putting them into mechanical testing machines. Therefore, it's also cost saving. We can save resources as we need less mechanical testing machines. They are all blocked in our company. Everything we have is full on their capacities. So it's really good to have simulation as another solution to be quicker with our testings. And at the end, we can also optimize our implants. So when we think about our standard implants, for example, and we want to figure out maybe which thickness might be the best for a specific indication. Previously, we have maybe printed a 1.0 millimeter and a 1.5 millimeter thickness plate, try them out, and then we say maybe 1.0 is the best one, and we go with that. But maybe there's another option which we just haven't produced. So with simulation, we can also plan thicknesses from 0.5 to 4.0, simulate and get a better understanding which is the optimal thickness we need to go. And this gives us just more possibilities with simulation to be quicker and to have a more broader view on product development. Now the second question, why do our customers need simulation? Because of physical limitations. So this little friend here has problems with reaching the ball he wants to play with. If you think of an example for surgeons, although the majority of surgeons are pretty good, and they are even better if they use KLS Martin products. But however, they still sometimes face some problems with physical limitations. So for example, using an intraoral approach to try to reach the condyle, maybe sometimes as a surgeon you feel like that little dog here. Therefore, we want to help reaching that ball, and we want to help them with simulation. So previously we weren't able to predict the outcome of surgeries, predict the movement of bones or the behavior of our implants. And with our simulation brand IPS inSilico, we want to create a world where it is possible to predict the outcome of surgery. So I would say that the really long-term goal with that technology with IPS inSilico is to give our surgeons the possibility to simulate every surgery in the beginning on a computer before they go into the OR and do the surgery there, so they already know what will happen before they go into the surgery. So then a quick look on the strategy of IPS inSilico. What are we planning, or why we are working with simulation from a more marketing point of view or strategic point of view? For those who know our company, we are, I would say, famous for our plates and screws, especially in the CMF area. That's our bread and butter business. We make most of our income with that, and this will never change. But you can talk with surgeons, and you quickly get the feeling that it's from time to time getting more difficult to distinguish yourself from other companies with only plates and screws. So you are somehow limited there in the field of innovation, or try to differentiate yourself from the competition. Therefore, we started finding a way where we could distinguish again from our competition, and that's with patient-specific products. So we are using IPS products that all of them are made specifically for the anatomy of each patient individually, combine that with software solutions to also plan patient-specific, which again brings us in the position to be a bit ahead of our competition. But we are now by far not the only company who is providing digital planning solutions, and therefore we need another innovation. And that's why we came up with the idea of IPS inSilico. So we are combining now our IPS solutions as well as our standard solutions with simulation to bring our products on the next level and to differentiate again from our competition to just go the next step here. All right, then we already had a look on that page in the morning. Just quickly through it an overview where we use simulation right now. So we use it in product development. We use it for the RPE software for treatment planning, for virtual implant testing with our IPS implants, as well as supporting diagnosis and therapy with the OSA software. So I think I can rush a bit more quicker on the different tools, as you already get some insights on that from Jan in the morning and also in his first speech, and also Raimund talked about that. But just to sum it up, the RPE software, where we change the way of treating, change the way of surgery. So we are facing the problem of having asymmetric widening here, and changing that by setting optimized cuts, so simulated different cuts. Here we are in a close relationship to the surgeon. So in web meetings, our IPS engineers define where those cuts needs to be. So roughly need to be from the height. Then we are simulating those 100 results. We are coming back with 5 results that are possible or that will create a symmetric widening. Then from our point of view, it's difficult to choose one of those 5 options, as we at KLS Martin have never cut real bone in the surgery. So there again, we need our surgeons. We talk to them, show them the 5 different options that are available, and then they can choose the one which suits them best for the surgery or for the patient. So all of them create symmetric widening, but you need to check it again from a surgery point of view. We already have seen those guides, so we do the planning in consultation with the surgeon. He approves the planning, and then we are producing those guides here and transfer them into the OR. So we have here then the cutting area as well as the positioning area with the screws of the RPE distractor. Secondly, the VIT software, so the software for virtual implant testing. Here, the problem we were facing in the beginning was that when you compare our standard implants with our patient-specific implants, there's a big difference in testing those implants. So if we develop a new standard implant, we can do mechanical tests on them. We can do mechanical tests on hundreds of implants to really make sure that they are documented, they are standardized, they are approved to make sure they can withstand the forces we are calculating with. But for our IPS implants, this is not possible, as there is a need to plan those implants, produce those implants, and ship them to our customer within a time slot of about 2 weeks, 3 weeks. And as you can imagine, there's definitely not the time, and especially also not the money to produce every time 2 IPS implants, to just use 1 IPS implant to break it then on a testing machine. And to solve that problem, we can here work with the VIT software to really make sure that our IPS implants can withstand the forces that are in the patient, that are acting in the patient. So that's an example. So again, the free prosthetic example, we have seen that in Jan's session already, so I can click through it. So these are the differences. Maybe what might be interesting is how we use that to talk to our surgeons, because sometimes surgeons have specific point of views, or maybe in that example, the surgeon could say he don't want, as you can see it in the left picture, in the second design, he don't want to use another bone stabilization, so another bone connection, because of course it will make the approach for the surgery bigger, it makes the surgery longer. So there are surgeons then coming up maybe with the suggestion to just remove that bar to be quicker, or to have it less invasive then. So in that case, we can use the VIT software also for argumentation. So it is way more easier if you talk to surgeons and you can really show them results that are saying, okay, we need that additional bone connection. Otherwise, there's a high risk of implant failure. And that's definitely nothing a surgeon or the patient wants. So we have made good experience with using those pictures to use it for argumentation why our IPS implants are designed as they are. We also, that's a second big benefit for the surgeons or for the clinics, that we can also use those simulations to support them in studies. So each surgeon is really interested in publishing, producing new studies or further develop, and it helps a lot to use simulation in a first step, or also to analyze a lot of cases read-through perspective to get a better understanding. And we really made good experience here to use simulation to support study to improve the relationship and also our image with simulation. That's then how it looks in a process. So that's our typical IPS process. We start with a new case. It is uploaded by the surgeon. We then have the planning process and the approval process, then the production, and at the end, the shipping. And we added now the phase of planning and approval with IPS inSilico VIT. So our IPS designer are using VIT to plan the software, so it helps to verify the design, and as I said, can be used for explaining or for argumentation with the surgeon. Then last but not least, the OSA software and how we use it or how we want to use it. I guess I don't need to explain it that much. As you probably know, we have a software called IPS Case Designer, where we can plan orthognathic surgery, and Raimund already explained that quite well. So we can move the maxilla and the mandible forward or backward, and that obviously has an influence on the airway. And we can then include the OSA simulation to our IPS Case Designer software to get a better understanding on which impact the movement of the upper or lower jaw has on the airway. So these are then at the end the results. We already have seen them with the pharyngeal resistance index in a three-dimensional view or in a map. And then you can also check the different parameters like pressure, velocity, and geometry. All right, that's it from my side. Thank you very much for your attention. There's definitely more to come in the future, but that's what we can present so far. Thank you very much.
So thank you very much for the introduction and also for the invitation. So my name is Anselm Stark. I'm currently doing MD PhD under Professor Christoph Gönig in the field of cardiology at the inSilico in Bern, Switzerland. And today I would like to present to you application of patient-specific computational fluid dynamics in anomalous aortic origin of a coronary artery. So the general structure will be that I will shortly give an introduction about the clinical problem. Then I will talk about the systematic review we did to assess what currently is out there as evidence. And in the end, I will present our current project. So anomalous aortic origin of the coronary artery, or AOCA in short, is an inherited and rare disease. Can you see the mouse? No. Then on the top, you can see a normal anatomy where you have the heart muscle basically, and the right coronary that comes from the right side, and the left that comes from the left side. And if you focus now on the image below, you can see that the right coronary comes from the left side, or it could also be the other way around. The left would leave from the right side. So in military recruits and athletes that died during strenuous activity, this specific anatomy was actually present in 1/3 of all cases. However, this does not represent the risk of people living with AOCA, since in recent years we do a lot more cardiac imaging and the incidence is constantly rising. Patients are more often middle-aged and asymptomatic, so the question is this an incidental finding now, and should still all patients receive an operation? So it's definitely important to look beyond anatomy and also do functional assessment in these patients. So the most important thing is that the anomalous vessel runs inside of the aortic wall, and I indicated this in red And the problem is that this part inside of the aortic wall is firstly, it is deformed and elliptical. And I try to demonstrate that when aortic pressure increases, which typically happens during physical exercise, the part inside of the wall gets compressed. So all of the tests we do with our patients focus on first resting conditions, and then we simulate exercise conditions with a drug, and we reassess the patients. So you can see that the heart rate increases between the two tests from around 77 to 150, and the blood pressure from around 114 to 140. And one of the tests we do is actually quite comparable to how we treat myocardial infarction. So we come with a catheter through the artery in the arm, then we go to the heart and we put a little wire inside of the vessel, and on top of this wire we have attached an ultrasound probe. So we are able to look inside of the vessel when we pull it back and look at the area of the vessel. And then we do this for rest and stress, and we can actually see in this patient example where the area drops from around 8 square millimeters to 4.5 square millimeters. Further, we also measure the pressure drop over this stenosis, which we call fractional flow reserve, or FFR in short. And for the 33 patients we assessed so far, we could see that pressure significantly drops from rest to exercise, and the area decreases significantly from rest to exercise, therefore proving this lateral compression. And additionally, you can see with the red dotted line, the values below, so only a small part are actually hemodynamically relevant and need operation. So this is still a very expensive and uncomfortable procedure for the patient. And here, computational fluid dynamics or fluid-solid interaction models could be a valuable alternative to predict flow in these patients. So first, we did a literature review to assess what has already been done. 19 studies were included in the final analysis, and we split them into dedicated CFD models and general purpose CFD models. And what we meant with dedicated CFD models is there is software out there which can predict the FFR, so the pressure drop, based on CT images, but the only user input allowed in this software is basically doing the segmentation of the geometry. Otherwise, you can't touch anything of the simulation. So 12 studies use this approach, and 5 case reports actually validate their results with invasive measurements. And it's a small sample size, but the results were not significantly different. However, this definitely cannot show this lateral compression, so the model is unable to do that. So the general purpose CFD models basically included every other approach to build a CFD model, and we compared them based on a standard workflow for CFD. So first, we need to create some kind of geometry based on patient images. Here, I would mainly like to focus on the image modality used. Then a mesh is created on which boundary conditions are applied. Here, I want to say something quickly about mesh optimization, blood parameters, and then CFD or FSI, and a quick note on microvascular resistance. And then the actual flow is calculated with the use of a specific software. And from these obtained results, the desired parameters can then be extracted. So basically pressure, voltage, stress, which then should be validated against some kind of clinical data. So 7 papers use this general approach and 6 use the CCTA. So it's a CT just for the coronaries, and 1 group used CMR, so that's MRI, but for the heart. And here I want to stress that the image resolution is actually crucial, since this is a very fine structure with a small area. And I wanted to demonstrate here how the image resolution of the image modality influences the geometry. And on the left side, you can also see a shell created from the ultrasound images on top, where we can also show the heartbeats. And on the bottom, we have the CT images in the same patient. For mesh, not much was reported, and mesh-independent studies were only performed in 4 of the studies. And for blood rheology, mostly a Newtonian model was used, even though blood is non-Newtonian fluid. And this is valid for normal coronary simulations. However, if this can be applied in anomalous patients is so far not known. And one thing I really want to stress here again is that 4 papers didn't do any exercise condition testing, but in all of these patients, these anomalies only can become relevant during exercise. There are no cases where there is a problem during rest. So one group actually brought everything together, and they already built an FSI model. So let's see why the video is not working yet, where they actually did the interaction between the aorta and the coronary, and they did that for rest and for stress conditions. Real quick note on the outlets. The microvasculature is actually very important for the hemodynamics, but we can't image that. It's very small. But you can see here on the left side, on the bottom, you see the flow for left coronary, and on top for right coronary. And the dark blue shows when the heart contracts. And when the heart contracts, the microvasculature also gets compressed, and the resistance increases a lot. So we have a changing resistance basically over one cardiac cycle. For post-processing and validation, actually only one paper compared the results to invasive measurements, while all the other ones used wall shear stress and vorticity magnitude, which can't be directly compared to clinical data. And the same FSI model I showed you before, they validated their data, and you can see with the blue dots that for resting condition, the model worked quite well. But as soon as we went into the exercise condition, which is important, as I stressed before, the variability increases a lot. So in conclusion, I think we can say that currently no model can predict hemodynamic behavior in these AOCA patients. And this is especially true for this lateral compression during these exercise conditions. So what are we currently working on together with SimQ? So first we built a CFD model that should predict the FFR adenosine, which is basically the pressure drop in rest without the lateral compression. And except for the geometry creation, we have a fully automated workflow there. We can do static or transient simulations for either coronary or aortic root together with coronaries. And the focus here was really to get a fast simulation, which is not computationally expensive. However, this definitely cannot show the lateral compression since we still used rigid walls in this first one. What we have to do still is compare the pressure results from our simulations to our invasively measured pressure results. Then the second approach was to just build a finite element method model. So we try to only show the compression of the intramural segment. And for that, we use the mesh, which is a combination of the CT and the ultrasound images. And we want to compare the deformed model basically again with the ultrasound images and find the optimal material properties to correctly model patient-specific aortic tissue. And in the end, we hope to bring everything together and build a fully functional FSI model, which can do both and predict flow for rest and exercise conditions. So we can hopefully provide that for our patients. So thank you for your attention, and I'm looking forward to questions now or later this evening.
We have time for a quick question.
Perfect, yeah.
Is there any additional risk to putting a stent in the application where the vessel is in the wall?
I brought a slide for that. That's the very interesting question. There was only one paper published 10 years ago where they stented like 20 of these patients and had a very high restenosis rate. So currently everybody's blocked a little bit, but we started to still do stents in older patients where we don't want to give them an operation. But we had that in 3 patients now, and in one we also had already a bit of intimal thickening and restenosis. So I'm not sure if it will actually be feasible. But it would be an interesting topic again for simulations if you have a working model. Yeah.
Just because I don't know, so what is the surgery when stenting is the not as invasive method? So
brought another slide. I thought that people would be interested in that. So it's a smaller operation than for standard heart surgery, but it's still open chest surgery, not the full big cut. And then you have to open the aorta from the front, not fully, but still heart has to be stopped. And then the part inside of the wall, which makes problems, is basically just slit open, and these 2 flaps are attached on top and on bottom. So this is like the most used operation. There are some different operations, but this is the most.
it gives more room for the
yes, and the vessel gets round again when it leaves the aortic wall and is basically normal again. So we just don't want this compression anymore.
Okay, thank you so much.